Yeah, hello and welcome to our tutorial on distributed and efficient deep learning. My name is Wojciech Samek, and together with my colleague Felix Sattler, who would like to present this tutorial to you. So we will start with an introduction into this topic. Then I will present some techniques on model compression and efficient deep learning. Afterwards, we'll have a obviously virtual coffee break. And finally, my colleague Felix will tell you about distributed and federated learning techniques. Okay, so let me start with part one. So we have seen in the last years a real revolution in the field of deep learning. Today's systems are able to solve complex tasks in many domains, like images, text, speech processing, or even computer games. They are able to outplay humans, even human professional players. And one of the main ingredients for the success was, first of all, the large amounts of data which recently became available. So we train these models on millions of examples. We have data sets, huge data sets, which we can feed into these complex classifiers. Also, like the complexity of our models has increased over the last years. So we have seen models which became increasingly deep and complex. So in order to train these models, we need large computing infrastructure, and we have developed GPU cards which can handle this complex training. So you can see here on the x-axis, you see the operations needed to perform some prediction for different networks. On the y-axis, you see the accuracy for this image classification task, an ImageNet in this case. And we see that some networks, like VGG, require really huge amounts of operations for a prediction. And the size of this circle also like visualizes number of parameters. You can see that VGG, for example, has almost over 150 million parameters, which is really insane. Other models are slightly more lightweight, but still require a lot of operation and have also some millions, up to 100 millions of parameters. So we need some techniques to design more efficient architectures on the one hand, and also some techniques to reduce the model size. Because if you want to transfer these models over communication, in communication applications, over channels with limited bandwidth, for example, we need some efficient compression methods for neural networks to reduce the size of these models without sacrificing accuracy. Also, at the same time, there was a recent study which compared the amount of the carbon footprint of a deep learning model trained, for example, like a very complex transformer model with neural architecture search, which is trained nowadays for solving complex NLP tasks. For example, people compared the carbon footprint of these models with the carbon footprint of a human life on average, 1 year human life on average, or 1 year of American life on average, or even like one lifetime of a US car, including fuel. And you see that the carbon footprint of this deep learning model is much larger than, for example, the carbon footprint of an average human. So if this figure shows you that we need to reduce computational complexity. We cannot simply train deeper models, bigger models, and waste resources for that. So we need techniques to reduce the computational complexity at training time. Here's another example where you see a self-driving car, which is equipped with cameras and radar, and it generates around 6 gigabytes of data every 30 seconds. And in order to process this data, the self-driving car prototype uses approximately 2,500 watts of computing power, which is also like quite a lot. So in order to cool this amount of computing power, you need water cooling, specially designed water cooling. And also here you see that we need techniques, we need to make things smaller, more efficient, in order to deal with this with these in these scenarios. Things get even worse when we move to, for example, embedded devices, smartphones, IoT devices, sensors. These devices have very limited computational capabilities, computational resources. So if we want to really implement deep learning on device, we need to reduce energy consumption, we need to reduce memory consumption, we need to reduce storage of these networks. But this is not the only problem. Another issue is that data is often distributed. Data is often distributed, and privacy is a very important constraint in many applications. So we cannot expect to collect these data at a central server and train our networks on these kind of racks, computing racks. So we need to train things locally. We need to reduce the computational complexity at inference time, and we need techniques to robustly train our models on distributed data in a privacy-preserving manner. So instead of sending data, all the data from different parties to a central server, we need to develop techniques to train models locally. And then if we want to execute these models locally, we need to reduce complexity at inference time. So as you can see, there is a lot of need for efficient deep learning, for distributed deep learning, because many applications require have some additional restrictions and constraints, especially applications in the field of communication. So we cannot simply train and execute our models on a supercomputer or on a like really powerful server or in a cloud. We need to think about techniques to design more efficient architectures, to reduce the model size, to reduce complexity at training time, to reduce complexity at inference time, and to be able to train in a distributed manner. So these are many topics, and this tutorial will cover some of them. Yeah, as you can see, there is also like a large interest in this topic in academia and in industry. So we have seen many workshops, many tutorials on these topics at recent conferences like CVPR, ICML, NIPS, or NeurIPS. So this year I'm co-organizing a workshop at CVPR, joint workshop on efficient deep learning in computer vision, where we exactly like will look at these issues and how to design efficient networks, how to compress networks, and so on. Also, in the topic of federated learning, there is a large interest. The number of publications are steadily increasing. Also, like big companies are using federated learning technology in their apps, in their tools, to learn in a local fashion, in a privacy-preserving fashion. Another issue, which is even more important for this execution on embedded devices, is the integration of common architectures with some special chips. So industry startups are designing accelerators for deep learning. There's many work on designing special hardware, dedicated hardware to execute things in a very energy efficient manner, or at high speed, low latency. So this is a separate topic, but which is of course connected to the topic of efficient deep learning. And finally, there is an activity which I am personally also involved in, namely the MPEG group has started some initiative on compression of neural networks. So soon there will be a standard on compression of neural network compression. I will tell you about this later in the talk, and give you some insight what's the current status in this group, and where are we heading to. Okay, so this was the introduction. Normally I would ask you if there are any questions, but I think here in this virtual setting, I will just go on and we can answer. I will answer a question later at the live session. Okay, so let's talk about model compression and efficient deep learning. So this part will, on the one hand, discuss techniques, how to reduce the complexity of neural networks by model compression and efficient representation. So in the first part, I will give some background on source coding, on pruning, quantization, and then we will talk a bit about how to find efficient architectures, how to reduce the complexity in your architecture by some pre-processing. I will present several ways to do so. Then in the third part, we will go deeply into the discussion of a particular compression technique called the deep kabak, which is currently one of the selected technologies at the MPEG standardization. And finally, we will talk about efficient neural network representation. So somehow all these topics are linked, but I try to structure the talk in a way so that you can that I will also like stress some of the individual aspects of each of these topics. Okay, so pruning, quantization, and backgrounds. So in source coding, so source coding is a subfield of information theory that studies the properties of so-called codes. So what is a code? So a primary task of such a codec, of an encoder and a decoder, is to represent a signal with a minimum number of symbols without exceeding an acceptable level of distortion. So in some sense, what you get is you have some random process, P of W, which generates your signal, your inputs. Then you have your encoder, which encodes this signal into some, in this case, a binary representation B. And the encoder here consists of two parts, a quantizer, Q, and a binarizer, or a lossy part and a lossless part. Then this binary representation is fed into a decoder, and the decoder reconstructs the value Q. And the goal is, of course, as I said, is to get a good reconstruction. So to minimize the number of symbols, so minimize the bits you need to store the encoded symbols, while not exceeding a given distortion level. So mathematically, you can write this down as a rate distortion problem, where you have where you want to find a code so that the length of the code, the average length of the codes, LC of B, or the length of the average length of the code words, is minimal. At the same time, also the distortion between the original value W of your signal and the reconstructed one Q is minimal. So the distortion between these two should be minimized. And you have some parameter lambda, which trades off these two terms. And then, for example, in video compression or image compression, you want to minimize the distortion between the signals, between the original and the compressed one. And the rate term gives you some rate or some of your video or some rate of your image. So as we said before, B is a binary word or binary symbol. Is you get this from W by applying Q by quantizing W and then applying some binarization step. And you can reconstruct, you get the reconstruction Q by applying the inverse of your quantizer to your word. No, you get Q by applying the inverse, inverting the binarization process, and then also like inverting, or in some sense, inverting the quantization process. But the quantization process is lossy, so in most cases you cannot invert it perfectly. Okay, so I mean, if you can invert it, if you can invert the quantization process perfectly, then we are talking about lossless coding. So for example, like zip is a format which is lossless, which reduces the size of your data, but does not lose information. So if you have this property, if you have a lossless coding problem, then the rate distortion objective just simplifies into finding a binarizer that maximally compresses the input samples. Then you are searching over the binarizer, because your Q is invertible. And from information theory, we know certain things. There are some statements regarding the minimum information contained in a probability source. So for example, Shannon proved in his famous work that the minimum information required to fully represent a sample that has probability P of W is of minus P log 2 P of W bits. And with this we can compute the entropy over a sequence and state that the minimum average number, so the entropy is the minimum average number of bits required to represent any element. And the fundamental theorem of lossless coding tells you that any code you design, any lossless code you design, then the average code length for this code will be larger or equal this entropy term. So it cannot be below this entropy term, which I think many of you know. This is like a standard result from Shannon's information theory. But the cool thing is that we know that, so it's not a very loose bound. We know codes that are able to reach the average code length up to 1 bit of redundancy. So we know codes which are between this entropy bound and this entropy plus 1. So which just need 1 bit maximum of redundancy, and we even know how to construct them, how to build them. And Huffman coding is one example of such codes, such optimal codes. And for example, in Huffman coding, you construct these kind of trees where you start start with the symbol which has lowest probability. So for example, here you have 0 and 1 have lowest probability. This P of 0 is 0.01. P of 1 is 0.02. So you first assign some prefix to this codes, to these symbols, and then you merge them and sum up the probabilities. They have probabilities 0.03 together. Then you do the same by merging it with the next symbol, and so on. And so then you construct a kind of a tree where every symbol has a code word assigned. And you see that the symbol which is most probable, here in this case 7, has a code word with the minimum, with the shortest code words assigned. Which makes sense because then you need less bits to transmit. And here, by constructing these codes, we assume that we know this probability distribution, and if this is the case, and we can construct an optimal code. However, practically, these Huffman codes can be very inefficient, since this Huffman tree can grow very quickly for large input dimensions. So if the input dimension grows, this Huffman tree can grow very, very quickly. Therefore, people started using like scalar Huffman codes, which do not have this problem, but also have like a looser bound. So they are within the entropy limit and entropy plus n, where n is this input dimensionality, which, for example, for neural network, maybe not so efficient, because if you want to encode your weights, the parameters of a neural network, it can be on the order of millions. So the bound can be very, very loose. And an alternative which is also works very well in practice and is used. It's also other advantages, is using of arithmetic codes. Arithmetic coding produces only up to 2 bits more than the minimum possible code length of an n-long random process. So they are also very efficient and also have some good practical properties. Here's an example of an arithmetic coding process. So arithmetic coding consists of expressing a particular sequence as a sample of samples as a so-called coding interval. So here we want to encode the word of the binary string 1.10111, and you see, and in this case, this word would be encoded as index 4, or as binary string 100. 100 is kind of the binary representation of index 4 if you start with 0. So it's a kind of fifth index in this case, and you see that if this gray strip above this index shows you which original word you have encoded, because for example, for the first symbol, this is W0, there's a 1, the number 1 falls into this interval. For the second one, W1, the number 0 falls into this interval. For the third one, W2, the first number 1 falls into in this interval. And if you just look up which numbers fall into this interval above, into this gray interval, which is put above the index 4, you will see that this is exactly the word which we encoded. This 10111. And it's quite a complicated process how to determine these intervals. So I will not go into detail here, but you can quite efficiently decode this original symbol by just checking which numbers fall into the interval. And here in the binary case, it's even more efficient. Yeah, so in lossless coding, so good properties, desired properties are universality, which means that the code should have a mechanism that allows it to adapt to its probability model to a wide range of different types of input distributions. In other words, I mean, we often do not know the probability model beforehand, so we need to estimate it, we need to adapt it to our input data. And you will see later a code which is very adaptive, which is very good for these situations. It should be minimal redundancy, of course. It should produce representations which are of minimal redundancy, which are compressed. And it should have a high coding efficiency. Yeah, this universal codes, as I told you, they kind of start with a generic prior probability, and after seeing the data, they adapt to the data, they update this probability model, and then encode the input samples. So in this case, the probability model is not known a priori, so it has to be estimated first or updated first. Therefore, these codes have an efficiency which is usually worse than if you would know the true probability. So here the average code length of the code word is larger than the entropy plus some Palper-Kleiber divergence term, which kind of measures the fit between the true probability model and the one estimated at the decoder. Okay, so this was the lossless part, some kind of introduction into standard source coding. If you think about the lossy coding part, or maybe one step back, we had this problem of rate distortion or optimization, where we wanted to find a code which minimizes this expected rate distortion term. And finding this optimal code is in most cases NP hard. So the idea here is that we fix the binary map. So if we have in this process, if we the whole rate distortion part depends on both the quantizer and the binarizer, so on the lossy part and the lossless part. And if we fix the binary mapping, if we fix the lossless coding part, then we then we can optimize this rate distortion problem. So if we select the universal lossless code, then we just need to find a scalar quantizer Q and to optimize this rate distortion term. And here we just treat the scalar quantization and ignore vector quantization, which is more complicated and also is often not used in practice due to this additional overhead. So here the goal is that we want to find some quantizer and some reconstruction values, Q and Q inverse, so that this rate distortion term is minimized. And but we assume that our binarization map, our lossless part, is fixed. Okay, so there are many different options to do so. So, for example, scalar-Lloyd algorithm would give you, in this situation, a good solution. And the scalar-Lloyd algorithm, it approximates the average cove length of the quantized samples with the entropy of the empirical probability mass distribution. So it just kind of constructs the empirical, the histogram of the quantized samples, and then estimates the entropy based on and then estimates the average cove length based on that. And so then you have like this LC of B, which is this average, this code length of the symbol. And the Lloyd algorithm just does what this k-means clustering does. So it assigns the values to the closest cluster center. So it quantizes the inputs by kind of Q and in the one step, and then it updates the cluster center. So it updates the reconstruction values, Q inverse, and these steps are done in alternation, but the rate part, the code length, average code length, is kind of fixed in this case. Another very simple example, a very simple quantizer, is just uniform quantization. So for example, you can just say that I don't care about the rate term. I just want to have a good quantization using a step function. And here, if you do this very simple approach, if you want to quantize using a steps function, then you just have one parameter, namely the step size for your reconstruction values. And this is actually an approach which we will later refer to when looking at the compression techniques used in our MPEP initiative. Very simple uniform quantization. Another, which is maybe more advanced, which we also tried out, is to use CABAC. So CABAC is a context adaptive binary arithmetic coder, so kind of complicated arithmetic coder as a universal code. So we can use CABAC as a universal code and then just trivially minimize the sequential or minimize by sequentially quantizing the input samples. So if we have CABAC as an estimator of our code length, we can simply find also the quantization values very easily by solving this rate distortion term. Okay, so this was just a very brief and superficial introduction into this source coding literature. There is, of course, much more to read and to in this domain, and there are books, whole books on these topics. But here, I mean, we are not really interested in source coding as per se, but we are interested in compressing neural networks, finding a good representation, an efficient representation of neural networks. But we can use the same principles. However, in source coding, we are minimizing the distortion, for example, between pixel values. In image compression, we minimize this rate distortion problem between our pixel, input pixel, and the reconstruction of the quantized pixel. Whereas in neural network compression, we are quantizing and compressing the weights of the neural network, but we don't care so much about the distortion between the original weights and the compressed and the quantized weights. But what we care about is the distortion between our original prediction outputs and the prediction outputs which we get after quantization. So we want to measure the distortion not with respect to the neural network weights, but with respect to the outputs of the neural networks, the predictions. So this is a slightly different problem, but it also looks like a rate distortion problem. And also here we can assume that as before, we don't optimize over both the lossy and lossless part, but we fix the lossless part and just try to find a good quantizer. So in neural network coding, things are a bit more complicated because the distortion term is more complex, because the error may accumulate over the layers in a nonlinear fashion. So if you quantize weights parameter in the first layer, you may get a much stronger effect in the output. Also, in your network, there is no clear structure in the weight matrices. In video and images, you have high correlations between frames, high correlations between pixels, and people who utilize this or make use of these correlations to further compress. There is this concept of prediction coding, transfer coding, and for neural networks, it's unclear how to do this more advanced coding techniques, because there is no clear structure in the weights. And also, but on the other hand, the neural network setting is more flexible. There we can often, what people often do is fine-tuning after quantization, or fine-tuning after, also do some iterative things. One can also sparsify the network beforehand, or kind of also change the structure of the network to make it smaller. So maybe if you have like a network with 20 layers, maybe you can remove some of the layers or some of the neurons, and just by that make it smaller. So in the extreme case, the whole training process can be regarded as a coding step. There is this MDL principle, minimum description length, which tells you that if you want to, for example, communicate some labels Y from A to B, you could do this by learning a model, a neural network, for example, and encoding the model. communicating the model. So this would require LW bits, for example. And then you could also, with this model, you could try to predict the values. So instead of directly transferring the values Y, you could transfer the model parameters and predict the values on the other side and just encode or just transfer or encode and transfer the prediction error. So we have some paper where we kind of applies this kind of technique for neural network, where we call it like we kind of regularize the training process by having some entropy-based regularization term, and can make the neural network representation during training more smaller and more efficient. But of course, if you want to do it, if you want to introduce also structural changes, then things become very complicated quickly. And there is a whole field called neural architecture search, which deals with not finding like a very efficient also architecture, not only compressing the network as it is, but finding an architecture, the most efficient architecture for solving a certain task. And my last slide in this part. So I just want to tell you like how what we have talked about here is that MPEG is also like looking at these different techniques in our MPEG standardization process. There is one part which is related to technologies which kind of pre-process a network, make it, for example, more sparse, or apply some matrix decomposition to it to make it more compression friendly. So this is one class of methods which are applied. Here we assume that we don't have like a really structural change in the sense that we are not training a whole new network, a much smaller network from scratch, or by distilling. We want to compress the network given to us, but we can maybe also like make advantage of making it a bit sparser. Then we quantize. Then we quantize it in CE2. We have technologies for quantization, uniform quantization, codebooks, etc. Binarize things and also encode things in a bit stream. So encode things very efficiently using some lossless coding. So as before, we have like three technologies like this preprocessing, I call it preprocessing technologies, parameter reduction methods, quantization methods, and encoding methods. Okay, so I will now go over these different parts and just give you some hints and show you some of the work which is maybe interesting in these areas. But of course, I cannot give you a complete survey of these technologies, because this is like a huge field, and many papers, many people have been contributing to it. So I can give you just a short, limited view on these techniques. Yeah, so probably the most very popular technique is this net pruning, where you make your network, your architecture more efficient by pruning either weights or pruning the whole neurons, for example. And if you do that, then often you not only have a possibly smaller architecture, but you can maybe also require less computation. You can do inference faster because you don't need to do so many multiplications. And also, like, this pruned sparsified network can be also maybe compressed better with other techniques. So this is like one step which is often done to kind of as a pre-processing step of your compression. Of course, for that often you need some data, some training data or some validation data to prune your network. And so if what people do is, like, say, kind of for each element kind of somehow evaluate the importance according to the pruning criteria. So you need the pruning criteria, and then for every weight or for every neuron, you kind of evaluate the performance, the importance of this element, and then the sort, the magnitudes of all the layers throughout the network, and prune the least important elements. And optionally, you can also fine-tune to compensate the performance degradation which you have introduced by pruning. And you repeat this process, this iterative pruning, and stop when you are happy with the model size or you don't want to lose more performance. So this is like a very generic scheme. And as I said, there are many different ways or criteria to prune your network. So you can either, what people do is some Taylor expansion-based criteria, where you leverage a second-order Taylor expansion based on the Hessian metrics to select the parameters for deletion. Outwork like optimal brain damage can be looked up here. Or people use gradients for identifying the non-essential features, or just use weights. And if a weight falls below a threshold, then maybe it's also pruned away. Or people applied some different kinds of regularization. So there are really many ways to do so. And the recent one which we have proposed is using XAI, so like explainable AI methods to identify important or relevant elements. So LRP, layer-wise relevance propagation, is a method to identify this relevant elements in the network. So relevant with respect to the classification, for example. So just a few words about LRP. So I have also given tutorials on the topic of explainable AI. I've also recently co-edited a book on that. There is a lot of work about that, but just that you get the main idea is that LRP, kind of what it does is it decomposes the prediction f of x into relevances, and it constructs kind of heat maps where every pixel tells you how much it contributes to the prediction in the end. And it doesn't only do it for the input layer, but also for the intermediate layers. So LRP is, so you have your prediction in your network, and then you are doing a backward pass where you measure where you redistribute the relevances according to some rules, and measure what has been relevant for prediction. There's also some theory related to LRP called deep Taylor decomposition, and you can look it up in the book or in our other papers. Okay, so there are some results from the study which we did. So this is with fine-tuning. The red line is LRP, and the other lines are like these other methods. And you see that on all these data sets, LRP performed slightly better, comparable, but consistently better than the other methods. But there were not so much differences due to the fine-tuning. So the other method, even if they pruned away some element which was important, which should have not been pruned away, due to in the fine-tuning step, you can kind of correct this error. So in some other experiments which we did without fine-tuning, you see that the LRP solution, the red line, is much more stable. So whereas the other criteria, weight and gradient, really fail. So Taylor expansion is also quite okay. But so if you only have very little data for fine-tuning, so if you are not really able to, or if you don't have labels, if you have very little data, then LRP-based pruning performs very well, much better than the classical pruning criteria. But if you are allowed to do fine-tuning, then the difference, there is almost no difference between these different techniques. So this was just a short presentation of pruning. There is a lot of other methods, many different also regularization techniques to get sparse networks. Another line of work is for kind of increasing the efficiency of architectures, is either like a distilling approach where you have, for example, a very well-trained network, a teacher network, which is complex but is well-trained, and then you want to train a student network which is much simpler. So what people showed is that by applying some distilling, so just learning the soft labels of the predictions, integrating the predictions of the teacher into the learning process helps very much to learn good student networks. Another very recent topic is this neural architecture search, where you kind of really search over the space of architectures, and this is a whole field in its own, very popular today. So if you want to really train an efficient architecture, you need some special restrictions, and you can use these kind of techniques. Okay, so this was the one part where we discussed finding architectures. Another part, I told you, this is a compression. I will present the compression technique, which is part of this MPEG standardization, which we proposed. But before doing that, let me go back to the source coding view, which we had before. So we said that, okay, in neural network coding, we want, given a binary fixed lossless code, we need to minimize the distortion between, or the loss between the outputs of the neural network, or output distribution of the neural network, and not the weights directly. So here, y dash is the original output with w, with the true weights, and y double dash is the output distribution with the quantized weights, with q. And so we want to minimize this term, and one way to explicitly write it down is to measure it. So use Kullback-Leibler divergence is a distortion measure. And with that, we can even, if the output distribution do not differ too much, we can approximate Kullback-Leibler with the Fisher information matrix, also like well known in the literature. And we can even simplify things by just modeling the Fisher information matrix by its diagonal elements. So by only making it a diagonal matrix, we arrive at this rate distortion problem, which is a weighted rate distortion problem. So we have for every kind of term I, we have a weight. So I guess it should be there's few errors here on the slide, so it should be argmin and also like an expectation. Anyways, so this is what deep Kabak is. So our deep Kabak, which we propose for the MPEG standardization in the first place, was exactly this algorithm where we said, okay, we take Kabak as a universal code, lossless code. Kabak again stands for context adaptive binary arithmetic coding. It's a standard tool in video compression. And I will explain it in the next slides, but this is we take as a lossless coding tool. Then as a quantizer for the reconstruction values, we just take uniform quantization. So we just take a step size parameter, which we need to fit, or we need to set beforehand. And we have these weights Fi, which kind of tell us how much impact this distortion of this weight has on the output. Because in some sense, we wanted to minimize, as I said before, we wanted to minimize the distortion in the output. So we wanted to have a compressed network or quantized network which has a similar prediction behavior. And if we quantize the weights in the first layer of a neural network, it may have a large impact on the predictions due to some nonlinear accumulation effects. And this Fi, this Fisher information matrix element, kind of tells us how important is this weight for the prediction in the end. So how much can it be distorted in order to not degrade the prediction? And actually, there is some recent work on Bayesian neural network compression, where people have shown that they can, if they parameterize weight parameters as a Gaussian, they can get an estimate or like the standard deviation of this Gaussian. If they fit Gaussian, then the standard deviation of the Gaussian tells us how much we can perturb the weight to not have to have a limited effect on the output. And this is exactly what we want. So what we did in the first deep Kabak version is to use these Bayesian deep learning techniques to get this parameter. But later what we found out at some later point that we can even simplify the problem and just use a uniform quantization plus Kabak and get very similar results. So for the neural network compression, this weight parameter Fi and also like the rate distortion formulation does not seem to play a big role. So we also didn't expect this at the end, at the beginning, but we tested our algorithm on several deep models. So in this MPIC initiative, we have to report results on several models with several configurations, and this very simple uniform quantization plus Kabak approach works quite well. And you may ask yourself, so what is Kabak? Kabak is context adaptive binary arithmetic coder. So as an arithmetic coder, it's what you do is, for example, if you want to encode the number 1, which is represented, if you want to encode the number 1, you get the code 100. Why is that? Because you have to check, so the first decision you have to make is this SIG, this sign significance bit. So everything which is not 0 gets a bit 1 in the first place. Okay, 1 is not 0, so it gets a 1. Then you check the sign flag, the second one. So everything which is positive gets a bit 0. Everything which is negative gets a bit 1. So the number 1 is positive, therefore it gets a bit 0. And then the third bit which you need, third decision which you need to make is ups greater 1. So up, if the absolute value of the number which you want to encode is greater than 1, you get you set the bit 1, otherwise 0, and since 1 is not greater than 1, it gets a 1, it gets a 0, and you are done with the encoding. So this is how the encoding kind of works. So you need to make this decision and compare in which interval your number falls, and then you get the binary representation of your number. And so Kabak has the property that it represents each unique input value as a sequence of binary decisions. So as we saw here, then it has some context modeling, which means that the probability of each decision is updated on the fly by the local statistics of the data, which means you don't assume a probability distribution beforehand, but Kabak is kind of adapting. So it has some scan order, it scans the weight matrix of the neural network in some predefined order, and then it adapts to the probability distribution. And it applies some arithmetic coding, so it has minimum redundancy and high efficiency. And why did we came up with exactly this decisions, this significant bit, sign bit, absolute 1, absolute 2, and so on? Because so we kind of checked the distribution of the quantized weights, and its distribution, which is around 0, and this form which we use for deep Kabak is very flexible, so it adapts to any type of shape around 0, and only the values which are further away are encoded with an exponential column code. But these values are usually uniformly distributed, so there is no peak there. So this is what. So in this algorithm, this Kabak part is an important step which allows to compress the representation of your neural network very well, because it adapts to the probability distribution and it uses some advanced coding techniques to represent things very effectively. And yeah, here are some results. So for example, for VGG16, ResNet, and so on, and we can reduce VGG16, for example, from 550 megabytes to 8 megabytes without losing accuracy, and for ResNet in a similar fashion. And these were kind of older results. Here we have brand new results, which we are even better. So on the x-axis you see the compression rate, and the y-axis is the top one accuracy, and the compression ratio, and here like different variants of our algorithm with fine-tuning, without fine-tuning, with some other more advanced concept called dependent quantization. And you see, for example, that for ResNet, for MobileNet, you get really good compression ratios. Okay, so this was one part. Let's move to the last part of my presentation. So once we have encoded our network, or how to efficiently represent these networks. So it would be good to find the representation for the neural network which is efficient with regard to storage and memory, which is efficient with regards to inference complexity, for example, scalar products, and also with regard to energy consumption. One very simple approach is to use a fixed point neural nets, and people have shown that it works quite good. So when you get, if you reduce your from 32 bits to 8 points integer, you get a reduction in memory. You get often a speed up. It has some good. It fits well to some microcontrollers or some ultra low power embedded devices. And so this is one way to get some efficiency and speed and in terms of memory. And often you don't lose so much performance. So if you go to 8 bits, there is almost no effect on performance in many cases. And another work which I want to present here is formats. So neural networks are usually stored as a dense format. So if this is a weight matrix of a neural network, so a fully connected neural network, then if you would need to save every value, you would have 60 entries, for example, 60 times 32 bits. And then if you want to compute, for example, a scalar product between a row in this matrix and some vector, then you need to load all these numbers, and you need to multiply and add up and write this operation. So you need to perform some few operations to do this. And there are, of course, other formats. So when this matrix is quite sparse, so you have a lot of zeros. So by the way, this is the compressed, the quantized neural net. So assume you have done quantization, and then you have this quantized weight matrix. So one could also think of using sparse formats. So in sparse formats, you don't save every number, but you save just non-zero numbers, and you save some column index, and you need to save some row pointer. So you need to tell, for example, the W is the numbers which you save. So 3 is in the first column. so yeah, so this is number 3 is in the first column, so you start counting with 0. So it's kind of the second column here, and it's in the 0th row. So you start with the 0th row, so which is actually the first row, and then the next number is 2. It's in the third column. So if you start counting with 0, it's kind of the 4th column, and so on. So you kind of reference non-zero numbers. And then in this formats, you need kind of less multiplication and addition. And because you don't need to multiply with 0, and in the sparse formats, you can do the scalar product, the multiplication inside the sparse format, so you don't need to reconstruct back to your dense matrix. And what we have come up with is another format, which is called compressed entropy row format, because it works well for neural networks having weight sharing property. Here, after quantization, we see that many values are the same. So here in this example, you have just 0s, 2s, 3s, and 4s. So you have just a couple of unique values. And in this case, you have a weight sharing property. So you have the same values shared. And in this case, if you have many weights shared, for example, if you want to do the scalar product here, and in the second row, there is only 4th and 0, so you don't need to multiply with 4 every time, but you can do this trick. So you can first sum up all the terms which you want to multiply it, and then you just do one multiplication. So here, instead of multiplying a 1 with 4 and a 2 with 4, you could just sum up the a's, the non-zero a's, and then multiply the sum with 4 only once. This is a trick, and our format kind of exactly allows this. So it's a bit more complicated. It has some set sigma, which tells you what are the unique values. 0, 4, 3. So the most frequent value is 0. So it's kind of it's clear, but it's not referenced in the other column. For example, the column index, column I, has a 4. Yes, and so the value, because you ignore the 0, this is the most frequent element, so you don't need to encode it. You just leave it out and fill it and fill it later. So the second most frequent is the number 4. And this column I tells you that the number 4 is at the 4th position in the first row. So the 4th position is actually the 5th position, because we start with counting with 0. So you see that you have this 4 at the 4th position. And then the next column index is 9, which is the 10th position in the matrix. And if you count it, you can see it here. And then 11, which is the 12th position, and so you can see that this is like referencing the number 4, and then you have a pointer which tells you that there is a new row, and you have a pointer which tells you that now we start with a new number in this set sigma. Okay, but in the end you have less multiplications, less additions, and also like a storage gain. And we have also checked like in which area. So if you look at your weight matrices as a distribution of our values, then this distribution can be sparse or not. If you have a lot of zeros, then this will be very sparse, and the matrix will be very sparse, but the distribution will be very picky, around 0. So on the x-axis you have this p0 value, and also like on the y-axis you have the entropy of this distribution, and the entropy tells you kind of how uniform the values are distributed. And you see that if the distribution, if the matrix is very sparse, if there are a lot of 0 values, then the sparse format is the most optimal one. You see if the sparsity level is quite low, but the entropy is quite high, then the dense format is appropriate, because you don't have so much weight sharing. But in the area in between, where you have a lot of weight sharing, we don't have just one number, 0, which is very, very often. You don't have the sparsity property, but you have many shared values, then our format is the best one. And yeah, in our paper, we have also compared the storage complexity, time complexity, energy complexity for different models, and we get some gains compared to dense. For example, storage complexity, we get a gain of 14 times. We get a compression, we get 40 times more compression. And in terms of energy, also we get some good gains. And this is, everything is lossless here. So it's just the format. It's just the way you store these matrices and the way you multiply. So you don't change, you don't quantize. Everything is quantized before, and now here is about the lossless format. Good, that was it. Let me conclude. So we saw that efficiency in training and efficiency in inference is very important. We saw different techniques to compress, to prune, to represent networks. We discussed that there are different options, that fine-tuning plays a role, structural change, neural architecture search can give you more options than just compression. In practice, often hardware co-design is crucial. So you don't need only to compress your network, but you also need to adapt the hardware. And yeah, in our MPAL group, we are progressing with compression techniques, and we hope to also we target to bring also this compression techniques to other use cases like federated learning, where we also see some potential for these methods. So that was it. Here are some references for the papers. It's neural network compression, efficient deep learning, also federated learning, which will be covered in the next part by my colleague. And the slides and the papers are also available at our website, federated-ml.org. So thank you very much. I hope you enjoyed this lecture, and I think it's time for a break, time for coffee. Thank you. Bye-bye.
All right. Hello, everyone. My name is Felix Sattler. I'm a PhD student at Fraunhofer Heinrich Hertz Institute, and I will bring to you the second part of this tutorial. Now, in the first part of the tutorial, you have already learned a lot about the efficient training and efficient execution of deep neural networks. And in this second part now, which will be on distributed and federated learning, we kind of broaden our view and now consider collaborative learning systems where multiple learning agents jointly try to train one neural network under certain sets of constraints. And as we will see, all of these concepts that we've learned in the first part of the tutorial will also be important in this setting, because these distributed federated systems often contain mobile and IoT devices which are hardware constrained. So efficiency is also a very key concept in this second part of the tutorial. Yeah, right. Before we dive into the distributed training part, let's maybe have a look at the centralized training, and then we can contrast it to the distributed learning. So the paradigm which has been the dominant paradigm in the last decade, I would say, has been cloud machine learning. So I believe all of you know cloud ML providers like Amazon AWS or Microsoft Azure. And they follow an approach where, say you have a base of users and they all hold some data, and now you want to train a model on all of these users' data. Then in the centralized approach, data will have to be uploaded to a central server. The server then trains a model on all of this data, and this trained model can then either be sent back to the users that provided the data, or the model can be used in a completely different way. So this is what's mostly done right now, because of course it offers many advantages. You move all of the computation workload from the hardware constrained distributed devices to the central server, but it also comes with a lot of problems that are associated with the fact that data is gathered centrally. So the main problem probably is privacy. So in many cases, the data collected on, say, your mobile phone is highly privacy sensitive. So you wouldn't want to send personal pictures or private text messages to an online server to train machine learning models. Another big problem is ownership. So once the data leaves your local device, it's very difficult to track what's going on with your data, and this is another big problem of the centralized approach. Security, another big issue. If you look on Wikipedia for data breaches, data center breaches, then you will find a huge list of incidents where large amounts of personal data have been leaked by hackers to the public. And of course, every centralized system has this issue that it's a single point of failure. You just have to break in once, and then you can steal data from all users, basically. Fourth issue of the centralized approach is efficiency. So in many cases, the data that is used to train machine learning models is extremely large. If you're looking at streaming data, that mainly comes from a self-driving car. So then you have tons of sensors, and they all gather high-resolution data. And in many cases, it's just not possible to transfer all of this data to a centralized server. Now we can contrast this with the distributed or embedded machine learning approach, where, first of all, biggest difference is that no data is transferred from the user devices to the server. Now, you might ask, well, how is the learning done then, if the data is not transferred to the server? Well, it has to be done on device, of course. So all of the data processing, training, or running inference has to be done on device if no data can be transferred to the server. That, of course, means that every client creates its own model, but it doesn't end there. So, of course, we all know that these neural networks perform better the more data they have available. So there have been, so people have developed methods to basically allow collaborative training without sharing the data. And the idea behind this is to share the parameters of the model instead of the raw data. So in conclusion, the distributed or embedded ML data never leaves the local devices, and instead model updates are communicated. And yeah, this basically addresses and even solves many of the problems that the centralized approach has. As we will see, there's still some caveats. It doesn't solve all of these problems perfectly, but we're much closer to a solution to these problems. Yeah, so distributed or embedded ML comes in very different, in many different forms. One is federated learning. We're going to talk a lot about federated learning today. Peer-to-peer learning is a different approach where we don't have the centralized server at all. We get rid of the centralized server altogether. We have distributed training in the data center and on-device inference, which are also, so the last two are only roughly related to distributed ML, but a lot of the concepts are the same. So in all of these settings, we communicate neural network data instead of raw data. We actually give a nice little overview about all of these topics in our paper, Trends and Advancements in Deep Neural Network Communication. So, but as I said, in this tutorial, I will mainly focus on federated learning. So yeah, let's see what is federated learning. So I pulled up a definition that's given in a very nice a survey paper, Advances in Open Problems in Federated Learning by Peter Kairos et al. And so they describe federated learning as a machine learning setting where multiple entities collaborate at solving a learning problem without directly exchanging data. And the federated learning process is coordinated by a central server. So those are multiple entities collaborate, no direct exchange of data, and everything is coordinated by a central server. Those are the ingredients that make up federated learning. So yeah, why is this a big deal? Why do we talk about it? Well, federated learning is a very new field. The first paper on federated learning was actually published in 2016. And since then, there has been a tremendous growth in both academia and industry to growth and interest to use federated learning. So as you can see, the number of publications has more than doubled every year now from 2016. So I believe it's a very, if you're a researcher, it's a very very good time to step into this field and get your hands dirty and be part of this new privacy revolution that is kind of taking over the ML world. And if you're a practitioner, then yeah, you can see that there are many examples in the industry where federated learning has been applied successfully. So yeah, people are using it to predict hospital stay time and patient mortality. It's been used as part of medical imaging AI, and lately, Google and Apple have also launched products based on federated learning. So Google is using it in their mobile keyboard prediction. So if you use, I think Gboard, it's called, then it kind of the next word prediction, and it also offers some other other features that are based on federated learning. So yeah, this is I think it's a really good time to step into this field now. And yeah, now let's dive right in. Let's look at how this is done. So we still haven't answered the question completely. How is this federated training process going on? So imagine you have a very large base of users. So in this example, there are 6, but could be millions to billions. Every smartphone user in the world could essentially be a federated learning client. And we have one server that coordinates everything. So the federated learning is carried out in multiple communication rounds. And in one communication round always follows the same protocol. So the first step, the server selects a number of users. So in every round, only a finite number of users will participate. And then the server communicates an initial model update to all of these selected users. Next, the users perform iterations of stochastic gradient descent on the model updates that they've received using their own local data. And that results in updated models on every single user, which are then in the next step uploaded back to the server. And on the server, a global aggregation operation, which is often just parameter averaging, creates the next set of parameters, which are here indicated in pink. So this is one communication round, and in the next communication round, other clients will be selected and everything starts over. So this is the communication protocol. This is basically everything that is done. And yeah, the interesting thing is that it actually works, that it's possible to train machine learning models to the same accuracy that you would achieve in the centralized approach, but without all of these issues related to exchanging the data directly. Yeah, so there are 2 main settings where this is applied. One is this cross-device federated learning, where we're basically talking about IoT devices or mobile phones as the clients. So there you have a large number of clients. Only a fraction of the clients will be available at any given time, because you can only do this usually when the phones are charging and in an unmetered mobile network. Also, in this cross-device federated learning setting, you usually only have few data points per client, and the devices have very limited computational resources. So this is the Google and the Apple scenario. But federated learning can also be used in this what's called cross-silo scenario, where the clients could be, for example, different hospitals that have very privacy-sensitive data on their patients that they are legally not allowed to share with other hospitals. But they still might want to improve their machine learning models together with the data of other hospitals, right? So in this setting, there's only a small number of clients. Clients are always available. We have very large local data sets and strong computational resources. So there's already like a little bit of two settings that can be applied. But everything that I will talk about today applies to both of these settings. So yeah, so of course, with any new technology, there are a lot of challenges, and it's very exciting to be in this field today, because it intersects with a lot of other disciplines in a very fascinating way, and there are a lot of interesting intersections between these different areas. So communication is a big topic in federated learning, privacy, robustness, personalization, heterogeneity of the data, convergence, a lot of important fields that have to be looked at if you want to get it right. So I'm going to start out with the communication part, because this is maybe the most critical about the entire federated learning thing. So as I told you, every communication round of federated learning consists of one download phase where the server broadcasts a initial neural network parameterization to all available clients, and an upload phase where the clients send back their updated neural network models to the server. So yeah, in every communication round we have an upload and a download. And yeah, let's maybe take out our calculator and look at a little case study for how much communication there is in total in federated learning. So very simple equation, we just have to multiply the number of communication rounds with the number of parameters in the neural network. And this we have to multiply with the average code word length that is used to represent every parameter of the neural network. And then this will give us the amount of communication in upload and in download over the course of a federated training episode. So if you now look at a VGG trained on ImageNet, so yeah, like a very common neural network trained on a large but still common data set of images, then we're talking about 900,000 iterations until convergence. The VGG16 network has about 138 million parameters. And if we use the full 32-bit floating point representation for all the parameters, we need 32 bits to represent every one of these parameters. So if we put this into the equation above, then we get to a total communication of about 500 terabytes of data. And I don't have to tell you that this is completely infeasible from different perspectives, right? It's not energy efficient. It's nobody will be able to use this if it creates 500 terabytes of traffic per device we have to add. So this is a huge problem. And that's why people have tried to come up with compression methods. And these compression methods essentially tackle all of the components of the equation above. We will look at communication delay as a first method to reduce the amount of communication. We'll look at lossy and lossless compression methods. So let's maybe first look at communication delay. So this is the first time you see an algorithm. This is the simple distributed stochastic gradient descent, which would result in this huge amount of data traffic that I've just calculated for you. So here it would go as follows. So we have a certain number of communication rounds. In every communication round, we iterate over all participating clients. We compute a gradient of the current model with respect to a batch of data on the respective client. And then we send this up to the server, and the server accumulates everything by an averaging operation. So this is essentially completely, from a mathematical standpoint, completely equivalent from the centralized training, but doesn't require data to be sent around. But of course, very inefficient. So the first thing people came up with was this federated averaging algorithm, which essentially performs communication delay. So instead of only computing a gradient in federated averaging, a model update is computed by performing multiple subsequent steps of stochastic gradient descent. So by doing so, you can essentially bring down the amount of communication rounds by a factor of k, right? And then on the server, same thing happens. We average out the parameters that we obtain. So this should not be delta, this should be theta. Yeah, federated averaging, very nice idea, very useful. Has many advantages. First of all, super simple. You don't have to change anything about the entire algorithmic design. It reduces the communication frequency, which is advantageous in on-device federated learning. And it reduces both upstream and downstream communication. So it's easy. Yeah, it reduces both directions essentially. And it's also easy to integrate with privacy mechanisms, which we will look at later. But as we will see, it also has some disadvantages, but we will get to that a little bit later. So I can show you some simple convergence analysis of the federated averaging algorithm for convex objectives. So as you see, asymptotically, you get the term sigma over square root of t times k times n. M is the number of clients that participate per round. K is the number of local iterations, and T is the number of communication rounds. And so, as you can see, as long as you keep the product of the communication rounds and the number of local rounds constant, it doesn't change anything about the convergence rate. So this is really great. So you can, in theory, really scale up this k to as much as you want. But of course, at some point, this first term here will become the dominant one. So yeah, so you have to weigh this against each other. Very important, this only holds for IID data. So for data where all of the clients sample their data from the same data generating distribution. It's a very, very important detail. And we will see why it's important right on the next slide. Because here we see that the convergence speed actually drastically decreases with increasing heterogeneity in the data. So what's plotted here in this figure is there was used a Dirichlet distribution to decide the split of the data on the client. So basically, this parameter 100 here indicates that all clients are holding almost the same data from almost the same distribution, whereas here in this right corner, the data is extremely non-IID. So clients are holding very, very different types of data. So, and what you can see is that the accuracy achieved within a constant communication budget decreases drastically as you go down here from the IID to the non-IID. Yeah, and we also see that this effect aggravates if the number of participating clients. So the reporting fraction here is low. So yeah, so this is definitely bad news because in many real-world applications where the data is created on the devices themselves by the data generating process. So if I take pictures, they will probably be different from the ones that someone in Russia takes, like or whatever, or even from the pictures that my neighbor takes, because we might have different interests. We take pictures of different things and so on. So this heterogeneity in the data is a huge problem, and yeah, unfortunately, we found that it's also a huge problem with this federated averaging algorithm. So here You can see some more formulas. Yeah, you can find the details on this table in this very nice survey paper here. Yeah, but essentially you see that in all of these the K term doesn't really play a role once you have non-IID data. So it's much more difficult to reduce the communication in the non-IID setting by just ramping up the number of local iterations. Yes, so disadvantages of the federated averaging approach are bad performance on non-IID data and low sample efficiency, in the sense that yeah, the more non-IID your data is, the more local iterations you have to perform to get the same benefit out of it, which means a lot of computation on the local devices, right? So yeah, these were the pros and cons of communication delay. And now let's next look at lossy compression schemes. There are two main categories there: unbiased and biased lossy compression. So let me again pull up the comparison between distributed SGD, and now we can look at distributed SGD with compression. So the only thing that changes here is that the gradient that is computed on the local device is compressed using some compression function, and then only the compressed gradient is uploaded to the server. Yeah, and when it comes to these compression functions, people have come up with 1,000 different ways to do it. There's literal quantization, there's ternary quantization, people use the sign of the gradients, people only use the top K elements of every gradient and set all other elements to 0, low rank decomposition. So basically everything that you can think of from a compression perspective, you can apply to these gradients and then see what you get essentially. And yeah, the main distinction here is some methods are unbiased, some methods are biased. Now, what does it mean for a compression operator to be unbiased? It just means that, yeah, in expectation, the compression operator doesn't change anything about the input to it. Yeah, so for this group of compression methods, they are very nice to handle from a theoretical standpoint, because the convergence proofs are quite simple, I would say. Because essentially you always get this bound here, where the numerator in the dominant convergence term is the variance of the gradient estimator. So the more, essentially the trade-off is, if you want to compress more, you get more variance, and then you reduce the amount of communication in every single step, but it increases the amount of steps that are required to reach the goal. Yeah? So you always have to balance this variance of the gradient estimator, and of course there are some methods which are more efficient kind of in the way they yeah, distribute the variance, and some other methods that are less efficient. Another benefit of unbiased compression is the variance reduction property for uncorrelated noise. So if you use this compression operator on, say, 1,000 clients individually, then, yeah, by simple arithmetic, the noise reduces by a factor of 1 over n with the number of clients. So this is quite useful if in scenarios where you have a lot of clients and a lot of clients are participating in every communication round. Yeah. However, there are also issues with this unbiased compression approach, and these lay mainly in the application side, because it has been observed that these unbiased compression methods just do not perform as well as other biased compression methods do. So Here, this Atomo is what I would say the state-of-the-art unbiased compression algorithm for distributed training, and it achieves a lower accuracy at a higher data rate than these biased compression methods, which we will look into next. So biased compression obviously just means that the compression operator in expectation changes the input. So one very important thing about biased compression methods is that they do not necessarily converge. I mean, sure, if you just use any biased compression algorithm, of course, you cannot expect that you get any bounds on the convergence. But, and that's a very, very big but, they can be turned into convergent methods via a process that's called error accumulation. And the groundwork for this was put in Martin Jagi's group at EPFL, together with Sebastian Stich. So they really created very important theoretical contributions to the convergence theory of distributed training methods. So what is error accumulation? What is this key ingredient in making these methods converge? Well, so again, we look at the original distributed SGD, and the thing that changes now is, so we do the compression. This is our biased compression operator, but we don't forget the difference, right? Before we were compressing, and then all of the information that was lost by doing the compression was not saved somewhere. And this is the only thing that changes in error accumulation, is that the difference between the actual gradient that was computed and the compressed gradient that is here is added to a residual. And in the next communication round, we add this residual to the gradient that we've just computed. So what happens is the information lost by applying the compression is not lost forever. It's just kind of delayed in time. It's a different form of communication delay, but has other characteristics. So there's this key theoretical contribution by Stich et al., which says that for a compression operator, for a biased compression operator, which satisfies a contraction property, which is just this property here, this is given, and this is actually satisfied by most practically relevant biased compression operators, then we get this bound on the convergence. And the crazy thing about this is that this convergent bound is asymptotically not dependent on alpha. So the term here, which is the contraction constant of the compression operator. So this basically tells you that you can basically compress here. You can compress everything away, and as soon as you accumulate the errors, and as soon as this alpha doesn't become 0, or it doesn't become 1, as soon as this is ensured, you will still converge at the same rate, asymptotically, of course. So of course, if you make it very messy, then the other leading terms will take over, and the convergence will slow down. But yeah, it's really, really impressive theoretical result. So if you do a little comparison, and unbiased and biased methods. Unbiased methods, we have Turngrad, QSGD, Atomo. You will find the references to all of these on the website that we've put up for this tutorial. biased methods, gradient dropping, deep gradient compression, sine SGD, power SGD. So yeah, I think the important takeaway are these convergence proofs here, where the unbiased methods require bounded variance of the compression operator, and the biased methods make use of this K-contraction framework. Yeah, very nice. So now we've reviewed a variety of compression methods for federated learning and for distributed training in general. And we just thought to ourselves, well, how about just combining all of these methods together to get one huge, big compression method? And so we tried it out. We combined the communication delay with a biased compression methods, namely the top K sparsification, which we see here. And we additionally applied a binarization to also get not only sparsification but also quantization of the gradients to reduce the communication load further. And then on top of everything, we use the most efficient or mathematically proven most efficient encoder for these integer sequences, which is the Goulomb encoder. And we just put all of this together and ran it, and we were really amazed by the results that we've got. So here in this table you can see different neural networks trained on different data sets, so up to ImageNet scale with really state-of-the-art networks at the time, at least. ResNet 50 is still very huge and important neural network that's used in many applications. And what we found is that we could achieve the same accuracy basically, but reduce the amount of communications by more than 4 orders of magnitude. So yeah, really interesting result, I think. And yeah, so not a huge theoretical contribution here, but this just shows that we can really push down the amount of communication by a lot. Yeah, it's really really impressive, say. So we can get, if we started out with just 500 terabytes, then after compression we are now at only 50 gigabytes maybe, which is still too much, but for a smaller network this might be the difference between infeasible and feasible. Yeah, so yeah, in another paper we also applied this approach to non-IID data, and we found basically that we also outperform even more severely in the non-IID regime. So here you can see our method, for example, in the case where yeah, this is essentially a very a very heterogeneous setup where all of the clients only see one category of a data set, and in this setting we completely outperform the federated averaging algorithm within a fixed communication budget. We also look at different other important scenarios, which are especially important in this federated learning setting, and we just saw that our method performs very well there. Yeah, maybe also a short comment to the efficient coding. I know that Wojciech already talked a lot about this in the first part of the tutorial. So in our group, we also came up with this deep Kabak algorithm, which is essentially the best encoder for quantized parameter tensors. Comes from video coding, works very well, and we also applied it to federated learning, and it also performs quite decently. So yeah, so after this first part, maybe let's have a short break. All right, let's continue. So I've already told you a lot about communication in federated learning and how it is one of the most pressing issues that need to be solved to make federated learning widespread available. And we also talked about the convergence properties of different communication efficient federated learning algorithms. And we also looked at the convergence properties under different assumptions on the heterogeneity of the data of the different clients. What I'm going to talk about next is the issue of privacy. I told you that federated learning is private based on the fact that the clients do not have to transmit their personal data to a centralized server. However, if you're a critical thinker, you might have asked yourself, well, don't the parameter updates that the client sent to the server contain some amount of information about the data of the client? And yeah, sure, the answer is yes. And if you're not careful, then this can really lead to disaster, and all of the privacy guarantees of federated learning can be lost, basically. So there's this very interesting paper called Deep Models Under the Gun, Information Leakage from Collaborative Deep Learning, where the authors basically show that you can come up with a strategy as an adversary that can force different clients participating in the federated learning process to upload parameter updates, which are very revealing of the data that these clients hold. So in this scenario, you have different clients all holding face data, and they train some kind of model together. And the adversary, by altering the updates that it sends to the server, can actually force the victim to reveal this information here, so what the victim looks like. And the results are actually extremely good. So this means that there definitely need to be definitely other measures need to be taken in order to ensure that the privacy is protected. And yeah, this is actually quite a difficult problem because there are so many different vectors of attack. So if you think about it, first there could be external adversaries that may look at data communicated by individual clients. They might also gain access to the server and sniff around, look at the parameters that are laying there. But you also have to protect yourself against potentially malicious servers that are even more powerful because they have access to the entire parameter history of all of the clients. But as in the example that we just saw, could also happen that there are participants in the federated learning protocols or clients that are acting maliciously, and you kind of have to protect yourself against all of them. And yeah, different methods have been proposed. There are two main branches. One group of methods uses cryptographic techniques. So they encrypt the parameter updates and then use some kind of smart protocol to ensure that only the participants which really need to have access to the data can access the data. And there's a other group of methods which is based on differential privacy, and this is the approach which is actually favored by Apple and by Google in their commercial federated learning systems. And I believe that this is a very elegant way of quantifying privacy loss. So we're going to take a deeper look into differential privacy. However, this will only be a very small overview, and there are really nice resources online on differential privacy that we've linked on our webpage for this tutorial. So yeah, what's the idea of differential privacy? It's basically differential privacy allows you to quantify the amount of information that you give away when you release some kind of statistical information that you've gathered about a data set. So if you have a mechanism A that maps a set of data points to some output, then this mechanism is called differential private with parameter epsilon, if and only if this quotient of probabilities here is smaller than epsilon. So what's this quotient of probabilities? So D and D prime are data sets which differ in only one element. And the fact that this quotient here is smaller epsilon basically just means that the probabilities here are almost the same. This in turn means that solely by looking at the output of the mechanism A, it's almost impossible to distinguish the data sets D and D prime, which in turn means that you cannot really know whether the data point, which is collected in D prime, but which isn't collected in D, is in the data set. So it gives you a guarantee on what can be inferred about the data that was used in the mechanism. So in the federated learning setup, this mechanism A is the stochastic gradient descent training process, which results in these parameter updates, which are based on the client's data. So this is the definition. Now you might ask, well, how do we get these bounds? How do we know if something is differentially private? And there are actually very simple mechanisms that can make any function differentially private. So essentially, if you have a function that's not differentially private, you just have to add noise. There are different mechanisms. Here I've just put the Laplacian mechanism. So you add some noise term, and then you have to also scale this noise by the sensitivity of the function, which is basically just how much the function varies if you change something about the data set. And you scale it also by the epsilon parameter. And then this will give you a mechanism that is epsilon differentially private, which is, so you are able to quantify the privacy loss by the method. So in federated learning, this means instead of directly sending the parameter updates up to the server, you add some noise first and then send it to the server. Very, very simple idea here. And what's nice about differential privacy is that it comes with some really nice properties. One property of differential private mechanisms is that they are, that the differential privacy parameters are invariant under post-processing. So if you have some data and you apply a differentially private algorithm with privacy parameters, and then afterwards you release that data, anyone can do with this data whatever they want. They can apply whatever post-processing method they want, and still the privacy parameters will not change. So it's not possible to gain any more information after a differentially private mechanism has been applied. This is a really nice property. So that way you can really stop scratching your head, just release your differentially private parameter updates, and anyone can do with those updates whatever they want. They will not be able to reconstruct any more information. That's one nice property of differential privacy. Another nice property is that you can very simply accumulate the privacy risk. So in federated learning, we release data or like parameter updates not only once, but we release parameter updates basically every communication round. So in every communication round, the clients are sending out their updates to the server. So we need to know some way how to add up or how to accumulate the privacy risk. And this can be done very easily with the basic composition theorem, which tells us if we apply our algorithms, which are all differentially private with certain parameters to the data, then the total privacy loss is upper bounded by the sum of the privacy parameters themselves. So privacy loss is additive. And this is a worst case analysis. Better bounds can be found with smarter accountant methods like the moments accountant. This should be it to the privacy. I mean, you've now learned that it's not just sending the parameter updates instead of the data. You have to do a little bit more to get privacy. But the good news is that if you do this little bit more, then you can actually give privacy guarantees and ensure that your data is really protected, which is really nice. And interesting new avenue of research that has just recently come up is this intersection between differential privacy and compression methods. Because if you think about it, differential privacy adds artificial noise to the parameter updates to obfuscate them, while compression methods add quantization noise to the parameter updates to reduce the bit width. So in both cases, noise is added, and of course you might ask yourself, well, can't we use this quantization noise in some way to also get more privacy guarantees, right? And there's, again, good news. It's possible to combine the two approaches, and people have already published on this. So there's a really nice paper. It's called Privacy for Free, Communication Efficient Learning with Differential Privacy Using Sketches. So yeah, you should definitely check this out. I think this is a extremely promising direction of further research. Yes. Okay. All right. Okay, so now we've covered this privacy topic a little bit. There's still some two open topics, namely personalization and robustness. So, as I already said, federated learning environments are characterized by a high degree of statistical heterogeneity of the client data. This means that in many situations, learning one single model will not be optimal or might even be undesirable. So let me give an example. Say we have n clients, and these n clients have data that was sampled from n different distributions pi, x and y. Then two scenarios could hold. Either all of the clients share the conditional distribution pi y given x. In this case, usually one single model can be learned. And then we can talk about IID data if also P of X is shared between all of these clients. Or we can talk about non-IID data in the classical federated learning setting where P of X and or P of Y varies, but the conditional distribution is still the same. So the labeling process is the same over all clients. This is kind of the classical setting that a lot of people are looking at, have looked at. It's kind of well researched. But what's kind of a new hot topic in federated learning is this other setting here, where also PI Y given X varies. So this means that different clients assign different labels to the same data. So in which situations could this make sense? Say, for example, you want to train using federated learning a next word prediction system. So you have a smart keyword that predicts the next word that you're going to type. Then of course, different users have different typing behaviors because they have different interests, they use different languages. So maybe one person likes ice cream, another person likes Beyonce, and the third person likes cats. So if you want to provide a good next word prediction system to these different users, you have to personalize it in some way because one model doesn't fit the needs of all clients at the same time. Another more theoretic, more schematic view, say you have two clients, you have the blue client and you have the orange client, and you want to separate their data with a linear classifier. Then for every individual client, of course, it's very easy to separate their data here, but there's no configuration where you can separate the data of all clients with just one simple model. So what this would translate to in more complicated scenarios is maybe you have a machine learning classifier that is able to fit the data of one client, but that's just not able to fit the data of 1 million clients all around because the model is too simple. This is not too unrealistic because, as you know, the devices in federated learning are often severely hardware constrained, so maybe they can only train a very simple linear model. So these are two scenarios where training one single model might not be the best thing to do. So we came to address this issue, we came up with a method that we call clustered federated learning, where the idea is to group the client population. So say we have some clients here, and you aim to group the client population into clusters with jointly trainable data distributions, and then train a separate model for every single cluster, like so. But how can this be done? How can the different clusters be identified? This is the main task here. Well, all of these clients here send up parameter updates to the server, right? Why don't we just take a look at the updates? So this is a very simple learning problem where we have two different risk functions defined by two different data distributions, right? And we have some clients that have data that results in the blue risk function, and we have some clients that have data that results in the red risk functions. And now we are jointly training a federated learning model. Then what happens will be the following. So all of the blue clients want to go into the minimum of the blue risk function. All of the red clients want to go towards the minimum of the red function. Their updates, however, are averaged all the time. So the path that results is this, right? And starting from this next point in the parameter space, the next updates are computed, and the next average is made. While this is going on, here on the left, we will plot the cosine similarity here between updates from the blue cluster, and here in black between updates from the blue cluster and updates from the red cluster. And as you will see, as this goes on, as we perform more and more steps, we get to an equilibrium point where the parameter updates from the blue clients and the parameter updates from the red clients point into exactly opposite directions. And as you can see during this process, the cosine similarity between clients from the same cluster, so say the blue client or the red client, stays at a relatively high value throughout the entire procedure, while the cosine similarity between the updates from clients from opposite clusters goes down towards 0. Yeah, so we end up with the stationary solution theta star here, and there the the gradients point into exactly opposite directions. Phrased again, at every stationary solution of the federated learning objective, the angle between the parameter updates of different clients is highly indicative of their distribution similarity. So from this, we can deduce an algorithm, very simple algorithm actually. So first, we have to run federated learning until convergence to a stationary solution. This gives us the stationary solution theta star here. And then we just have to compute the pairwise cosine similarities between the latest parameter updates from all clients. So look at the gradients for all pairs of clients, compute the cosine similarity here. And then if there exists a client whose local empirical risk is not sufficiently minimized by the federated learning solution, so we're in this situation from the slide before. So we see the gradients are still too large to have, so we're not converged to a solution of the for all clients, sufficient for all clients. This is the case. Then we just simply bipartition the client population into two groups of minimal pairwise similarity. So we look for the bipartitioning to two clusters C1 and C2 that maximizes the pairwise cosine similarity. That minimizes the maximum pairwise cosine similarity, right? So, and then we just start over again and do everything from the start. And the nice thing is that we can actually prove that this procedure will give us the correct clustering of clients so that we are able to reconstruct which clients share the same P of y given x, so the same conditional distribution. Yeah, so some formulas, basically given a certain bound on the gradients of the risk functions in their quotient, we can show that if the number of clients k has a certain number, then we can prove that we can correctly separate the clients. So this is a visual yeah, it's a visualization of this result. So there's this area here where we can provably correctly separate the clients. And there's another large area where we cannot prove it this far, but by simulation we have shown that it still gives the correct clustering with a probability almost 1. So we also provide a more detailed experimental analysis. So you can actually measure the quality of the clustering with this function g of alpha here, which takes the difference between the minimum pairwise cosine similarity of 2 clients with the same data generating distribution and the minimum of 2 clients that were assigned to different clusters. And as long as this value g of alpha here is greater than 0, we know that we will always get the correct clustering from our separation method. And yeah, now it's very interesting to look at the different scenarios. So in theory, our theorem predicts that we can get the correct, that we can correctly separate out the different clusters only if we have converged to a stationary solution of the federated learning loss surface. But in practice, we find that this is possible already after certain number of communication rounds, a certain fixed number of communication rounds. So g of alpha here indicates basically the quality of the separation. We also find that we can do this when clients only hold very few numbers of data points. So at MNIST, we can get a correct clustering already if every client only holds about 100 data points. And what is quite important from a practical perspective is we can show that this, or empirically, this also works if we use weight updates instead of gradients. So this kind of shows that our theoretical results are maybe even too conservative and can also be extended to more practical regimes where we don't communicate gradients but weight updates instead. And it also already holds after a few communication rounds, and clients hold limited amounts of data. Yeah, so we had that. So yeah, when you perform federated learning, it's basically a recursive splitting up of the client population. So you start out with a certain population of clients, and you perform one split. If the clients within this certain split are then sufficiently similar with respect to their data distribution, the cluster federated learning process stops here. But for a different cluster, it could be otherwise, and this cluster could be separated even further and split up. So this basically gives you different layers of specificity. So if this client here, if you move down this tree of models, so every split here creates one model, then you will get here the most general model, and the models increase in specificity the more you move down this splitting tree, which also gives some additional advantage. So you could use multiple models at the same time, do an ensembling of different models of different specificity, or I don't know, in some situations you might want to use the most general model. In some situation, you might want to use a more specialized model. So this is another benefit that this method gives us. And yeah, of course, we ran some experiments here with a model on the CFAR data set, where we looked at 4 separate groups of clients. Every group of client contained 5 clients, and they all were holding separate distributions of data. And so this plot here shows basically the development of the accuracy over the period. After every 50 communication rounds, we performed a split of the clients according to the separation criterion of clustered federated learning. And as you can see here, every time a group of clients is separated out from the main cluster, the accuracy drastically goes up. So very nice empirical result also. Yeah, so in this ICASSP conference, we kind of extended this idea and also applied it to adversarial settings. So we already talked a little bit in the privacy context about adversarial settings. There can also be a lot of other adversarial settings where clients do not perform as expected. So maybe some clients can have like some software or hardware issues, which results in them sending up only corrupted parameter updates. The clients could also have some bug maybe in their data, which results in flip labels or something like that. And yeah, in this paper, which we have published in this conference here, we find that also in these scenarios, clustered federated learning is able to separate out the adversarial clusters from the main cluster of benign clients, which may improve the accuracy quite drastically in some situations. Yeah, so this basically concludes the second part of our tutorial. We've now covered all of these topics here. We talked about communication, convergence, privacy in the context of federated learning, and I just presented to you also a method to personalize federated learning more and to address, by this heterogeneous scenarios and make federated learning more robust. Yeah, so here are our works in the areas of neural network compression, efficient deep learning, and federated learning that Wojciech and I talked about today. You can find all of these references also on our website, www.federated-ml.org. There you can also find the slides of this tutorial and all other important related information. So yeah, thank you a lot for attending this tutorial, and I think we will now see each other and have a questioning round. So yeah, bye-bye.